let's define the dimension of a finite dimensional vector space V is the length of any of its bases. Okay. Now, for this definition to work, you have to know something, which is that this number does not depend on the choice of the bases. In other words, let's say if this has a length 3 basis, then any other basis that you choose should also be length 3. And we don't know that yet, so let's prove that. And that's 2.35, which is any two bases of V has the same length. And as I said, when we're discussing basis for a vector space, we are only discussing for finite dimensional. So if you have a finite dimensional vector space, then any two bases has the same length. Well, this is a direct consequence of 2.23, which was that length of linearly independent list is always less than equal or equal to length of spanning list. So let's say B1, which is V1 through Vn, and B2, which is W1 through Wm. We don't know if n and m are the same. N is the length of this guy and m is the length of this guy. Yeah. Are both bases. Well, since B1 is linearly independent, a basis is linearly independent, right? And B2 is a spanning list. So that immediately implies that n is less or equals to m by 2.23. Okay? Now what do? You switch roles, right? You're done. B2 is linearly independent, and B1 is a spanning list, which means that m is less or equal to n by 2.23. But how can this be? That means m is equal to n. Done. Okay. All right. Now the next, obviously, this theorem now justifies this definition. So we know that if you want to know the dimension of a vector space, then you only need to get one basis for it. So, for example, R3 now is definitely three-dimensional. We were talking about that by intuition and from our previous knowledge of the calculation-based linear algebra. But now R3 is, with this definition, it's definitely dimension 3 because you have the standard unit vectors, 3 of them, I, j, k, that spans R3. So it's three-dimensional. Okay? So that's how it works. Now, 2.38 says if U is a subspace of V, then dimension of U is less or equals to dimension of V. Okay. Well, proof. let V1 and Vm be a basis for U, right? And that's a linearly independent list. So extend to a basis in V. By extending means, I mean, it could end up being already spanning the whole thing. In that case, you don't need to extend at all. In that case, you end up saying that U and V are the same, right? If not, you can extend, then definitely extended list is bigger than the previous one, right? So that's immediate consequence of this argument. 2.39 and 2.42 let V be n dimensional. Okay. Now 2.39 says a linearly independent list in V of length n is a basis for V. And 2.42, a spanning list of length n is a basis for V. See, span, let's say you have this, let's say this list is V1 through Vn. So that's length n, right? The span of V1 through Vn is a subspace of V. Right? And now, because V1 through Vn is linearly independent, we can extend, right? To a basis. But if it gives a longer list, then what contradiction we get? The dimension of V is bigger than n, right? Because it became longer. So we can't extend, so that's it. Yeah. The extension you can do, so I guess this wasn't even necessary, sorry. That was not necessary. Just saying, you have this linearly independent list, you can extend, but if you extend and it has to be longer in order to span the whole thing, then you end up saying the base is longer than n, therefore the dimension is bigger than n. But that's contrary to our assumption, right? So it has to be exactly n, so that's it. So can you come up with an argument for this one? How would this one work? If you have a spanning list, what's the theorem? A spanning list always contains a basis, right? Yeah. But if, so let's see, V1 through Vn is a spanning list it contains a basis. You can take something out. Yeah. But if the resulting list is shorter, then the dimension of V would be less than it. So it can't be, right? So that's it.